Red. Gray. Any questions? Structs. We'll go through some examples to illustrate a couple of structs. And then at the end of the class, we'll start talking about the application in C, which is sort of one of the key things that's really in C and C++. On one hand, is Java.
Quick question. So the size of the struct is predefined.
Yeah, I'm going to come to that. So, if my question, if your question isn't answered by what we do over the next 20 minutes, then feel free to ask.
Okay.
So, any other questions? No, I've shut off my phone. So, here we have, in the middle there, the definition of 4 different structs. The one on the left, it's kind of a simple one. And the question is, what's the offset to J? So in that struct, what's the offset? Struct one. See a 4? Why do you say 4?
Because it's one integer down.
Yeah, so what does it mean, the offset? It means how many bytes are you from the beginning. And that relates to how many bytes of allocation is there before that. So in this case, the struct has two things, A and J. A comes before J. Therefore, J couldn't possibly start sooner than 4 bytes. And that the offset of J is 4. Now, if we look at Y, it's a little more complicated. So in Y, we have in I struct A star S and int J. And again, we want to know what is the offset to J. Well, let's start by listing the size of the things that are before J. So what's the size of this? 4. What's the size of that? Okay, not 4. 8. But it could be 4. It's 4 or 8. It depends. It depends on whether the machine that's executing this is a 32-bit processor or a 64-bit processor. All modern processors are 64-bit processors. Now, they also support 32-bit mode, so it's actually possible to run programs that have 4-byte pointers compiling on these machines, although that's sort of being phased out. It's no longer possible on Mac. But one reason that you might say 4 is if we're doing this in assembly language in SM213, assembly instruction set architecture, there we have 4-byte pointers. Because there, that's a 32-bit machine. Pointers 32 bits, takes 4 bytes to store 32-bit pointer. But if you're on a machine like you all are right now, it's your phone that has 64-bit pointers, then to store a memory address requires 8 bytes. Okay. And there'll be come a time when we may ask you a question that to get this question right, you have to know whether this is 4 or 8. And we'll always tell you. And if there's ever a time we don't tell you, then you can choose either 4 or 8. Just let us know. Right? So it's not like 4 was the wrong answer. It's just that it would be very uncommon for these things usually be. And then this also is 4, although that doesn't matter in computing the offset. So now the question is, well, first of all, what's the offset to I? 0. So now I want you to discuss with each other what is the offset to sorry, and let's do this one. Well, what's up the offset to S? What's the offset to J? Okay, so what do you think offset to S? Here's an 8. Here's a 1. 4. Any other numbers? Let's take the following markers. What about 1? Who said 1? Why 1?
In pointer arithmetic, it's like offset by 4.
Ah, so you're thinking offset is an index.
Yeah.
Yeah, so I'll try to unambiguously use the word offset to refer to byte offset. That's what I mean here, byte offset. Index will, of course, now depend upon index into what. So if it's an index into an array of integers, index 1 is equal to byte offset of 4. So you said?
Yeah.
You say 4. Does that make sense? Yeah. Okay. So what about 4? So we had 4 in it. Why 4? Who said 4? Why 4? Right. So we know that, so when this is in memory, let's do like this. So there's each of those is a byte. So there's the 4 bytes of I. And so this is at offset 0, 1, 2, 3. So the next variable spot is 4. Right, so it could potentially go there. But let's now look at an example where, say, this whole thing starts at address 1000. So if this is an offset 4, offset 4, what's its address? 1004. What's wrong with that? Who said that? Right. It's not a line. If this is an 8-byte thing, the compiler will generate code to access it using instructions that will load all 8 bytes at once. And that requires that this address be aligned to 8. But it's not aligned to 8, it's only aligned to 4. So this is wrong. It has to be what? 8. So what goes here?
Nothing.
So here's where S starts. What goes there?
Empty.
I don't know. It's nothing. Just wasted space. We need to waste it so that this starts at the right alignment, so that when you access it, you access it on address. And because of the way things are listed here, there's no other choice but to make that have that space be wasted.
Struct A is always fixed that just regardless of how many things are actually within it, because the pointer always has the bytes.
Yes. So this is just a pointer.
Yeah.
All pointers have the same size. It doesn't matter what it points to.
And so does that make the compiler always realign everything to the largest space available?
Yeah, that's exactly what it does. So I'm going to have a piece of code here we're going to look at. Example, I posted to Piazza on Wednesday an extended example code. There's also an assembly code file as well that you can use if you're not sure about this. Later as you're doing an assignment after class on the weekend when you're bored, to do some of the things that I'm doing Okay, so here I've got struct A and struct Y. So this is a pointer to that. And we want to know what's the address, what's the offset to S. So there's a couple ways I can do this. So let's first we'll allocate a variable. That is type pointer to struct Y. And then I will initialize it by allocating space for struct Y. And here I want to say size of something so that I get the right number of bytes. What's the best thing to say? Well, one thing I could say is struct Y. Is that the best thing? Is there a single point of control here for the struct Y? No, there isn't, right? Because what if I change this variable? Now, I guess since they're on the same line, maybe it's, in that particular case, it's not so bad. But better, that's what we talked about last class. This. And that really is only important if it's something. More important is like this. And then that initialization or sign of the variable when they're actually on the same line. As I said, your answer's fun. Because here I've got struct Y. That is kind of sort of same line. So I'm going to do that anyway. And then what I'm going to do is I'm going to print out some things. So %p will print a pointer in hex. And I want to print out the address of A, Y, arrow, I. So that's the address of the first thing. And A, Y, arrow, S. Yeah. So I'm going to get the address of this, which in this example is 1,000, it's not going to be 1,000, and the address of this. And I'm going to use this to see what the offset is. The offset will be the difference in bytes between here and here. And now there's another way to print out the address of I. What is that? So here I have this variable AY. With points here. Here's the struct. The address of AY is the same thing as what? AY arrow I. Well, in this picture, what's the value of AY? 1,000. So the value of the pointer gets me here. This is at offset 0, so the address of this is the same as that. So just to verify that that's really true, illustrate that. I'm going to print that as well. Okay? So I'm going to print the value of that, the address of that, and the address of this. Now, here's that file. Let's edit it. I'm going to compile it. Right, that's running the C compiler. Now, what have I got there? Now, because I didn't specify an output file, it created an executable in a file with one name, a.out. Right? So I can run a.out like this. And you see that's the value of the pointer, that's the address of A sub I, and that's the address of AY arrow I, and that's the address of AY arrow S. You'll see these two are both the same, and this is in fact 8 bytes away from that. If I instead did this, and gave a name and it puts the executable in the file with that name. And I can also put these on the same line, separate them by semicolon. Now, the file that I'm executing is called a.out. What is the dot slash all about? Yeah, it's specifying the directory. So dot means it's a synonym for the current working directory, and slash is what separates the directory name from the file. So what I'm doing here is listing what's called a path name, rather than just a command. In a shell, when you type a command, like this, ls, for example, or gcc, what's happening is the shell has been initialized with a list of paths for all the executable programs. Now, ls is running a program named ls, which you can find out which one it is by saying which one. And what the shell does is it looks through all the executable files and all the paths and creates a cache, creates a database, a hash map. Okay. So when you type in the command, it knows which one you run. But it doesn't update that hash map when you make new files. And so if I just type a.out, unless a.out has been added to that hash, which you can do, you can say rehash name to be added, then you don't need the dot slash. Then it's going to take that name not as a file name, but as a command in a whole file name. But by putting the dot slash in front of it, now it's going to interpret it as a path name. It ignores that database, and it just looks in the file system for that file. So that's why, I mean, this is going to be, when you're fooling around, I don't know, I think a.out is an incredibly stupid name, but I just gotten so used to it now. I don't, it's like, because I don't want to have to say minus O. And you'll see later, actually quite soon we'll be using makefiles to build things, and so you won't be typing this directly, and then you'll get executables with useful names. But this will be quite common, the dot slash a.out, or dot slash foo. Questions about that? Just a little aside on the shell. Okay, so another thing that I can do here is that C has, so we have size of, which is a built into the language static command, sort of like a function, that the compiler, that you can use to ask the compiler what is the size of something, and so long as it has a static size, the compiler will tell you what that is. There are two other ones that we're talking about now. One of them is offset of. With offset of, what you do is you give the name of a struct and something in the struct. So that says, what's the offset of I in struct Y? And what should the answer be?
8.
Zero. Put a new line there. Comment that out. And if I say, what's the offset to S, what should I get? 8. And so now, if I say, what's the offset to J, which is really what the question was about, what's the answer?
16.
Offset to this is 8. It's 8 long. So the soonest place it could go is 16. It has to be aligned to 4. 16 is aligned to 4. The answer is 16. Questions about that?
Is there no way for the compiler to figure out that the space between 4 and 8 is big enough that it
Space between,
like empty space like between I and
this empty space?
Yeah. And not like just stick J in there.
Yeah, so what you're asking is, why doesn't the compiler do it like this? be offset 0, offset 4, offset 8, no wasted space. That would be better. But in C, the layout of things within a struct has to be preserved. And the reason for that is that structs are sometimes used in a way that the programmer requires that you do, that certain things be at certain places. Now, it's actually quite rare, but remember that C was initially built to build operating systems. In an operating system, sometimes a struct has to map to a hardware-defined data structure where the actual position of things, which byte they're in, is required. And so, in order to have that ability, the language compiler compiles the struct, it's going to lay them out in the order you listed them, with no exceptions. Now, if these were just global variables, the alignment property still also holds for global variables, but the compiler will reorder global variables, or even local variables, just not things absurd. It's a good answer. Good question. Also good answer.
If struct A was an int and a char, it would still have an offset of 8, correct?
It doesn't matter what's in struct A. It matters is the size of the pointer. I'm going to come to another example about this in just a second. Let me, I want to do something else though first, is that these semicolons are required, and if you don't put the semicolon there, you get an error. Okay, just take that semicolon out and try to compile this. I get an error, you've got to have semicolon. And the reason for that is that after this type declaration, it's allowed to list variables, to declare variables. And so I could do this. And declare the global variable AY. And so when the compiler sees the squiggle bracket, it keeps looking until it gets to the semicolon to see whether you've listed any variables there. And also I could do this, I could say, I could have another thing, B, Y, C, Y, B, Y. And you'll notice that some of them have stars and some of them don't. And this gets to kind of a weird thing about C, is that when you declare variables on a line where multiple variables are listed separated by semicolon, there's a type on the left-hand side. And the star really relates to the type. It's either struct A or struct A star pointing to the struct or the struct itself. But when you have multiple variables, you put the star with the variable. So what this actually does is declares AY and CY to be pointers, and BY and DY to be the actual static struct. And it's the same thing as if I did this with an integer. If I say int, and I can have star A, B, star C, D. Okay? So that declares two integers, B and D, and two pointers to integers, A and C. And so this kind of gets to, I've been doing that to emphasize the star as part of the type. But really more because of this, if you have the commas there, more properly, that's really bad. Any questions about that? Okay, so let's now get to the back to the slides here. And I have now this one's structure, slightly different. Here, instead of struct A star, I have a struct A. So what I want to do is I want you to lay out what this looks like in memory. So I'll start off, we have int I. I'm just going to list the names. So we have, to start off, we have I, size, offset 0, size 4. And now the question is what comes next? So discuss that with each other. What comes next? So what comes after I in this struct? Somebody doesn't know. Anybody know? Well, what comes next is the whole struct A. Struct A is included in this struct. So what comes is the first thing in struct A, which we could write like this. S dot A, and then we have S dot B, and then we have J. Now, this is struct A. Does that make sense? It's just included in the structure. Same thing would be if I had a static array. It's included as part of the structure. Size of all these are 4, they're all integers. What's the offset to this one? 4, 8, 3. Questions?
Wouldn't it be like 18 the size of it? Because it doesn't actually know it.
Thank you so much. So the question was, why isn't this aligned to 8? Because the total size of the struct is 8. And the reason why is that you never will be accessing the whole struct together. You're going to access just this or this. I mean, actually, you could access the whole struct. But what's important is that these things be aligned. And so what the compiler does is it takes that struct and just takes the inside of the struct and puts it in, and then figures out what needs to be aligned based upon the individual types. And the types here are either going to be int, sorry, we'll start char, short, int, long, or something star. 1, 2, 4, 8, usually 8. And those are the only sizes that matter for alignment. So if you have something that's bigger, the compiler will generate multiple instructions. All right, so what about this one? Here I have struct Z, and inside of it, it references itself. Struct Z star. Does that bother anybody? Usually bothers lots of people. Why does it bother you? It seems like it's infinitely recursive. Okay. How many of you are in 21? Ah, so you know what a linked list is, right? So if I were to draw a linked list, maybe it looks something like this. I have a singly linked list of integers. Does that look familiar? Okay. If you were to describe this type, let's call that an element. How would you do that? In C++ or in C? Yeah, but how would you write that down in the programming? Class. Okay, so you might say this. You might say class element int value, and then what comes next? Element next. Okay. Now you can also do that as a struct. You can also do that as a struct. So what's interesting here is that this variable next, if I asked you what's its type, you would say, well, it's pointer to an element. But actually, technically, that's not true. It's actually pointer to an element or null. Because sometimes pointers don't point to things. Now, this solves the infinite recursion. Right? Because in a linked list, eventually, so here's one of the values of next, pointer to one of these things, one of those next pointer to one of these things. But this value of next is null. And so long as you eventually get to null, or of course it could be circular, that's also not infinite. But then I think it kind of makes sense. But in most programming languages, this notation always implies that the pointer could be null. And if you try to use a null pointer, you get an error. Is anybody in 310? So in 310, in TypeScript, which is the language they're using there, TypeScript actually differentiates between these two things. There's something called a nullable type. Have you guys done nullable types? So you can say it can't be null, or it can be null. Right? So technically, the type of that is struct, element star, or null. But that's implied in C and C++. So, big picture here, it's perfectly fine. It's super common to have this sort of thing. This is just going to be an element, a node, that can possibly store a pointer to another node, or it could be even itself. It's not useful. But it is like you have a list of one thing that might be helpful. Right? Everybody good with that? But what if I do this? That's not okay, right? Because how big is this? Well, the compiler will start to lay it out and say, well, the value, that comes first. The next thing is an element. So remember what it does. If there's no star here, it's going to put that right inside. It says, okay, what's an element? Oh, it's a value. And then there's an element. Well, what's an element? A value. Right? And you